But previously, in one of our lessons, kind of in the second part of this unit, we talked about how to multiply polynomials, and we looked at special cases. And one of those special cases was difference of squares, and we had the result of the answer that kind of looks like what we're going to be dealing with. So remember, factoring is going backwards. So if we see an expression, a polynomial expression that we know is the difference of squares, we should be able to start recognizing what the factors are a little bit easier. So I'm going to dive right in. A difference of squares. So we're going to start filling out this little definition. A difference of squares refers to a polynomial of the form a squared minus b squared. So that's a squared minus b squared. Or, well, you'll have to excuse me. I'm not using the same pencil that I normally do, so I might make a few mistakes. Or a squared value subtracted from another squared value. So that's the a squared minus b squared, or a squared value subtracted from another squared value. If a polynomial begins as a difference of two squares, the a squared minus b squared, we know that its two factors are a plus b and a minus b. So our a terms are squared, but our a term and our b term are the same, but our signs are different. So we know that that's our two factors. So we're going to look at some examples of possible squares. And so what we're going to do on this next little part is we're going to write either yes or no if it is a square to identify whether it is a perfect square. And if it is, we're going to write what number we squared to get it. So for 81, yes, it is a perfect square because 9 times 9 is 81. 144, that's yes again, because we know that's 12 times. Why does it erase that? 12 times 12. X squared, yes. That's x times x. 9x cubed. Well, we know that 9 is the square of 3 times 3, but x cubed is not a perfect square, so that's no. And then 4x squared. Both of those, the coefficient and the variable, are perfect squares, so that means we can take the square root of both of them. So 4 is 2 times 2, and x to the fourth is saying x squared. Remember your rules of exponents, your properties of exponents. And if we multiply 2x squared, you're adding those exponents. So if you want to figure out if this number is a perfect square, divide by 2 and see if if it's an even number, it's a perfect square. Okay, so let's practice. Okay, x squared we know is a perfect square. So we know that our a term is x. We know that we're adding and then subtracting. And 49, the square root of 49 is 7. 7 times 7 is 49. Why does it keep erasing? So I know that my two factors are x plus 7 and x minus 7. The reason why I know this is because this was a difference of square. It was the a squared minus b squared format. So those are my two factors. Okay, number 2, we can take the square root of 4b squared. Go ahead and set up my parentheses. That would be 2 times b plus and 2b minus. and the square root of 25 is 5. Now, some of you are maybe wondering how I'm getting these numbers. I'm taking the square root of both of those. You can either put the number in the calculator with the square root, then the number, or it might be helpful to go ahead and write down a chart or like a little, just something down in your notes that's all the different perfect squares, like 1 times 1 is 1, 2 times 2 is 2, 3 times 3 is 9. Go ahead and write those out. I would say at least up to 15 or 20, just to kind of help you start memorizing those. So when we are practicing this, it might save you some time. Okay, 3. I'm going to take the square root of that number and the square root of that number and divide my exponent by 2. It's pretty much the basics of what I'm doing. So I know that the square root of 36 is 6 and m squared plus and 6m squared minus, and the square root of 1 is 1. So those are our answers. Okay, so now what we're going to start looking at is maybe some situations that we have all of the above, all of the different types of factoring that we've talked about. We've talked about greatest common factors. We've talked about polynomials with a leading coefficient of 1 or a leading coefficient of something else than 1. And now this is our new form. So we're still going to have to look for a greatest common factor. That should be step 1 anytime that you factor. So let's go look at number 4. Looking at this, I know that 6 is not a perfect square. There's nothing that's a number times itself to equal 6. But I also know that if I can take 54 and divide it by 6. So I'm going to do that. That's my greatest common factor. I'm going to take out a 6, divide by 6, divide by 6. That leaves me with n squared minus 9. Now, what I'm left with is a perfect square on both a term and b term. I know that those are a difference of squares. So now I know what my factors are. I have 6n plus the square root of 9 is 3, n minus 3. So all of that, those are my factors. Now, if you want to double check this, the easiest thing you can do is just go back and multiply your polynomials and then multiply by your greatest common factor to see if it comes out with the same answer as you started with. Okay, now looking at number 5, once again, 3 is not a perfect square, but I know that I can take 3 out of both terms. So I'm going to pull that greatest common factor out, divide by each term by my greatest common factor. That leaves me with c squared minus 4. That leaves me with a difference of squares, 3c plus 2 and c minus 2. One more practice. I'm hoping that you're understanding that this is probably one of our easier type of problems to factor, but it will be difficult if you are not recognizing your perfect squares. Okay, looking at this, 8 and 50 are not perfect squares. And I can't really pull out 8 from 50, but they're both even numbers, so I know I can at least pull out 2. So I'm going to try that. And I also can pull out a p, as that both terms have a p. So I'm going to pull my greatest common factor is going to be 2p. Divide that. That leaves me with 4p squared minus 25. And that is a difference of squares. So 2p, the square root of that first term would be 2p plus the square root of my second term is 5, 2p minus 5. So that is factoring using difference of squares. So let's do kind of an applied problem. The kids' pool in Ben's neighborhood is rectangular shaped and covers an area that can be represented by 169x squared minus 64 units squared. Write the expression to represent the dimensions of the pool. Okay, so it says it's a rectangular shaped area that covers. So we need to factor out. We're going to factor out. But it's already a difference of squares. We don't have a greatest common factor, but both of those are squares. So my expression would be we're writing the expression to represent the dimensions of the pool. So its area, we're multiplying, so that's why I know to write the two factors. The square root of the first term is 13x plus 8 and 13x minus 8. All I'm doing is taking those two terms. I know they're perfect squares, and I'm taking the square root to figure out what my a term is and my b term is. So that is difference of squares. You can go ahead and start working on your